Hello and welcome to Bedtime Black Holes channel. Tonight we drift in the quiet depth of black holes. Imagine floating peacefully in space, witnessing the final moments of a massive star's life. Our story begins not with darkness, but with light. The brilliant life of a massive star, at least 20 times heavier than our gentle sun. For millions of years, this stellar giant burns peacefully, balancing the inward pull of gravity with the outward pressure of nuclear fusion. Like a cosmic dance of opposing forces. But even the most magnificent stars must eventually exhaust their fuel. When our massive star can no longer sustain nuclear fusion in its core, gravity wins the ancient battle. In less than a second, the star's core collapses from the size of the Earth to just 12 miles across. Imagine compressing all of our planet into the space of a small city. This collapse happens so violently that it creates temperatures of 100 billion degrees. That's 6,000 times hotter than the sun's core. Yet, paradoxically, this incredible heat signals the birth of the coldest, darkest objects in the universe. The core becomes so dense that a teaspoon would weigh as much as Mount Everest, creating a gravitational field so powerful that nothing, not even light itself, can escape. Picture this transformation as a gentle metamorphosis, like a cosmic butterfly emerging from its stellar cocoon. But instead of wings, it unfurls invisible tendrils of curved space-time. As we drift closer to our newborn black hole, we encounter an invisible threshold that defines the very nature of reality. Around every black hole lies an invisible sphere called the event horizon. Not a physical surface you could touch, but rather a boundary in space-time itself. The name comes from the fact that no events occurring inside can ever be observed from outside. It's like a one-way mirror made of gravity, where information can enter but never leave. The size of this invisible boundary depends entirely on the black hole's mass. Following a beautifully simple relationship discovered by Carl Schwarzschild in 1916. For a black hole with the mass of our sun, the event horizon radius of just 2 miles. But for the supermassive black hole, at the center of our Milky Way, weighing 4 million times more than the Sun. This boundary stretches across 15 million miles. Time itself behaves strangely near this boundary. As you approach the event horizon, time slows down relative to the outside universe. To a distant observer watching you fall in, you would appear to freeze at the edge, your image growing redder and dimmer until it fades away completely. Even though, from your perspective, you continue falling normally into the darkness below. Imagine time flowing like honey near the event horizon, thick and golden, while far away it rushes like a mountain stream. Now we venture into the deepest mystery of physics, the very center of our black hole. At the heart of every black hole lies something called a singularity, a point where our understanding of physics gently breaks down. Here, matter is compressed to infinite density, and space-time curves infinitely, creating conditions so extreme that Einstein's equations whisper. I cannot describe this place. And quantum mechanics responds, neither can I. Yet, black holes are not the cosmic vacuum cleaners many imagine them to be. They only consume matter that ventures too close, within about 3 times their event horizon radius. Our sun, if it magically became a black hole tomorrow, which it cannot, being far too small, it would have the same gravitational pull it has today. Earth would continue its peaceful orbit, though our days would certainly become much colder and darker. Perhaps most remarkably, black holes slowly evaporate through a process discovered by Stephen Hawking in 1974. They emit a gentle radiation like cosmic psi, caused by quantum fluctuations near the event horizon. For a black hole with the mass of our sun, the process would take longer than 10 to 67 years. A number so vast that the age of our universe is but an instant in comparison. Picture these cosmic giants as patient gardeners of space-time, slowly tending to the fabric of reality with their invincible hands, reshaping the very geometry of existence. Picture yourself as a photon of light, traveling at the ultimate cosmic speed limit, yet finding yourself trapped in an invisible web. Even though light has no mass, it feels the pull of gravity, because black holes actually bend the fabric of space-time itself. Imagine space-time as a stretched rubber sheet. A black hole creates such a deep depression that even the straight line paths of light become curved, like marbles rolling around the edge of a funnel. There exists a magical distance around every black hole called the photon sphere, located exactly 1.5 times the radius of the event horizon. Here, light can actually orbit the black hole in perfect circles. If you could somehow position yourself at the distance and look sideways, you would see the back of your own head as light behind you travels all the way around the black hole to reach your eyes. As light struggles to escape from near a black hole, it loses energy and becomes redder, a phenomenon called gravitational redshift. Light that started as brilliant blue near the event horizon would appear deep red to distant observers, like cosmic sunset that stretch across the electromagnetic spectrum. Imagine these photons as tired cosmic messengers carrying news from the edge of oblivion. These colors fading as they climb out of gravity's deep well. Now, we witness one of the nature's most spectacular light shows. Matter spiraling into the cosmic abyss. When matter falls towards a black hole, it doesn't simply drop straight in. Instead, it forms a swirling disk called an accretion disk, like water spiraling down a cosmic drain. As this material orbits closer and closer to the event horizon, friction heats it to millions of degrees, causing it to grow brilliantly across the entire electromagnetic spectrum. These accretion disks can shine brighter than entire galaxies, making black holes, paradoxically, some of the brightest objects in the universe. The supermassive black hole in the galaxy 3C273 outshines our entire Milky Way galaxy, by a factor of 100, despite the black hole itself being completely invisible. The material in accretion disks doesn't fall into the black hole immediately. It can orbit for thousands of years, slowly spiraling inward like leaves on an autumn pond. Some particles gain so much energy from the magnetic fields in the disk that they're actually flung away from the black hole at nearly the speed of light, creating brilliant jets that stretch for millions of light years. Picture these jets as cosmic lighthouses, beaming energy across the universe, announcing the presence of these invisible giants to anyone who knows how to look. As we delve deeper into the black hole physics, we encounter one of the most profound puzzles in modern science. According to quantum mechanics, information can never be truly destroyed. It can only be transformed or hidden. But when matter falls into a black hole, what happens to all the information it contained? The argument of atoms, the quantum states, the very essence of what made that matter unique. Where does it all go? Steve Hawking initially believed this information was lost forever when black holes evaporated, creating what physicists call the information paradox. This would violate one of the fundamental principles of quantum mechanics, suggesting that either our understanding of black holes or quantum theory must be incomplete. Recent research suggests that information might be preserved in incredibly subtle correlations in the Hawking radiation, like a cosmic library where every book has been shredded into individual letters. But the story can still be reconstructed if you're patient enough to decode the pattern. This process would take longer than the current age of the universe, making it practically impossible, but theoretically preserving the scared principle that information is internal. Think of this as the universe's way of keeping perfect records, even in the deepest, darkest. Every story that ever was continues to exist, written in the quantum foam of space-time itself. Imagine floating high above our Milky Way, watching as invisible forces guide the dance of hundreds of billions of stars. At the heart of nearly every large galaxy, including our own Milky Way, lies a supermassive black hole containing millions or billions of times the mass of our sun. Our galactic center hosts Sagittarius A star, a gentle giant weighing 4.3 million solar masses, sitting quietly 26,000 light years away, orchestrating the slow waltz of our entire galaxy. These supermassive black holes didn't grow by swallowing stars one by one. That would take far longer than the age of the universe. Instead, they likely formed from the collapse of the very first massive stars in the early universe, then grew by merging with other black holes and gradually accreting surrounding gas over billions of years, like cosmic snowballs rolling through time. The mass of a galaxy's central black hole is mysteriously connected to the total mass of stars in the galaxy's central bulge. Following a precise mathematical relationship, this suggests that black holes and their host galaxies grow together in a cosmic partnership, each influencing the other's development through processes we're still learning to understand. Picture this relationship as a gentle cosmic marriage, where galaxy and black hole dance together across billions of years, each partner helping the other grow and evolve. Now, let's explore what would happen if we could somehow journey closer to one of these cosmic giants. If you were to fall feet first toward a black hole, you would experience something scientists poetically call spaghettification. The gravitational force at your feet would be significantly stronger than at your head, stretching you vertically like cosmic taffy. For a stellar mass black hole, this stretching would begin when you're still thousands of miles away from the event horizon. Paradoxically, larger black holes are gentler to fall into. The supermassive black hole at our galaxy's center is so massive that you could actually cross its event horizon without feeling any unusual stretching at all. The tidal forces that create spaghettification are inversely related to the black hole mass. The bigger the black hole, the more gradual the gravitational gradient. These same tidal forces that would stretch a human also explain why we don't see large objects orbiting close to the black holes. Any moon, asteroid, or planet that ventures too close gets torn apart by tidal forces, creating a disk of debris. This distance, called the Roche limit, varies for each black hole, but typically extends several times beyond the event horizon. Imagine these tidal forces as invincible cosmic hands, gently kneading the fabric of space-time, sculpting the region around each black hole with mathematical precision. Despite their fearsome reputation, black holes are surprisingly inefficient at consuming matter. Black holes are incredibly picky eaters. Matter must have exactly the right trajectory to fall directly in. Most material that approaches a black hole actually misses it entirely, swinging around in hyperbolic orbits and flying back out to space. Only about 1% of the matter in a typical accretion disk actually falls into the black hole. The rest is eventually blown away by radiation pressure. If our sun were replaced by a black hole of equal mass right now, Earth would continue orbiting normally. We wouldn't be sucked in. The gravitational field outside the event horizon is identical to that of the original star. We would freeze in the darkness, but our orbital dance would continue unchanged, following the same elliptical path we've traced for billions of years. The nearest known black hole to Earth, called Gaia BH1, lies specifically 1,560 light-years away, close enough to study with telescopes, but far enough that it poses no threat to our solar system. Even if it were moving directly towards us at incredible speed, it would take millions of years to reach us, and we would detect its gravitational effects longer before any danger arose. Think of black holes as cosmic hermits, sitting quietly in their corners of space-time, affecting only those who venture very close, while the rest of the universe continues its peaceful dance around them. In the vast coldness of space, we encounter something remarkable. Black holes that are somehow both the coldest and hottest objects in the universe. Black holes have a temperature even though they appear completely dark. This temperature is inversely related to their mass. The more massive the black hole, the colder it becomes. A black hole with the mass of our sun would have a temperature of just 60 billionth of a degree above absolute zero, making it colder than the cosmic microwave background radiation that fills all of space. Paradoxically, smaller black holes are much hotter. A black hole with the mass of a mountain would have a temperature of billions of degrees, glowing white hot as it rapidly evaporates through Hawking radiation. These tiny black holes would explode with the energy of millions of hydrogen bombs. Though none this small are thought to exist naturally in our universe. The temperature of Hawking radiation is so precisely calculated that it allows us to assign entropy, a measure of disorder, to black holes. Remarkably, this entropy is proportional not to the black hole volume, but to the area of its event horizon, suggesting that all the information about what fell into the black hole is somehow encoded on its two-dimensional surface. Imagine the event horizon as a cosmic hologram, where three-dimensional reality is perfectly encoded on a two-dimensional surface, like shadows that contain the complete essence of what cast them. As we peer deeper into the quantum nature of black holes, we encounter puzzles that challenge our understanding of reality itself. Recent theoretical work suggests that the smooth, empty space near the event horizon that Einstein predicted might actually be filled with a firewall, a region of incredibly high energy particles that would instantly incinerate anything trying to cross. This creates a paradox. Either Einstein relativity is wrong, or quantum mechanics is wrong, or our understanding of information is incomplete. The firewall paradox arises from the requirement that Hawking radiation must be entangled with the interior of the black hole to preserve information, but also entangled with earlier radiation to maintain quantum consistency. Since quantum particles can't be entangled with two different systems simultaneously, something must give away, leading to the theoretical firewall. Some physicists propose that the paradox resolves itself through black hole complementarity. The idea that what you observe depends entirely on your perspective. An outside observer sees the firewall, while someone falling in experiences smooth, empty space. Both perspectives are equally valid, like two sides of the same cosmic coin. Think of this as the universe's gentle reminder that reality itself might be more flexible than we imagine, where truth depends not just on what we observe, but on where we stand to observe it. Now we encounter one of the most profound insights in modern physics. The idea that our entire three-dimensional reality might be an illusion. The holographic principle, inspired by black hole physics, suggests that all the information contained in a volume of space can be encoded on its two-dimensional boundary. Just as a hologram on a credit card appears three-dimensional, but is actually stored on flat surface. Our entire universe might be a projection from information stored on a distant boundary. This principle emerged from studying black holes and has led to remarkable discoveries in theoretical physics, including the ADS CFT correspondence, a mathematical duality that shows how gravity in the interior of space is equivalent to quantum field theory on its boundary. It's as if the universe has multiple, equally valid descriptions. If the holographic principle is correct, then every black hole is like a cosmic hard drive, storing vast amounts of information on its event horizon. The information isn't lost when matter falls in, it's simply encoded in an incredibly complex pattern on the black hole's surface, waiting to be slowly released as Hawking radiation over astronomical timescales. Picture our entire reality as a magnificent cosmic hologram, where every point contains information about the whole, and black holes serve as the universe filling cabinets, keeping perfect records of everything that has ever been. Imagine time as a gentle river, flowing smoothly until it encounters the gravitational rapids created by these cosmic giants. Near the black hole, time dilates dramatically due to gravitational effects. If you could hover just outside the event horizon of a stellar mass black hole for what feels like 1 hour to you, when you return to Earth, you might find that decades or even centuries have passed. This isn't science fiction, it's a fundamental consequence of Einstein's general relativity, confirmed by countless experiments. The closer you get to a black hole, the more extreme this time dilation becomes. At the photon sphere, that magically orbit where the light can circle the black hole, time passes about 40% slower than it does far from the black hole. At twice the event horizon radius, time cools by at roughly half the normal rate compared to distant space. This time dilation creates a beautiful symmetry, while Hawking radiation causes black holes to slowly evaporate over cosmic time. The time dilation near the event horizon means that, from the black hole's perspective, this evaporation happens much more quickly. The black hole experiences its own death in a different time frame than the rest of the universe witnesses it. Picture time as honey near these cosmic giants, thick, golden, and flowing slowly, while far away it rushes like a mountain stream, carrying the universe forward at its natural pace. Now we turn our attention to one of the most elegant phenomena in physics, the way black holes can make space-time itself sing. When two black holes spiral into each other and merge, they create ripples in space-time itself, called gravitational waves. These waves travel at the speed of light, carrying energy away from the system and causing the black holes to spiral inward faster and faster until they finally collide in a cosmic crescendo that can be detected billions of light years away. The first direct detection of gravitational waves occurred on September 14th, 2015, when the LIGO detectors felt space-time stretch and compress by less than 1 to 10,000th the width of a proton, as waves from two merging black holes passed through Earth. This merger, which lasted just 0.2 seconds, converted 3 solar masses worth of matter into pure gravitational wave energy. These gravitational wave detections have revealed that black hole mergers are surprisingly common, occurring roughly once every few minutes somewhere in the observative universe. Each merger creates a new, large black hole that settles into a perfectly spherical shape within milliseconds, like a cosmic droplet finding its natural form. Imagine space-time as a vast cosmic ocean, usually perfectly still, but occasionally disrupted by these magnificent collisions that send gentle waves rippling across the entire universe, whispering stories of distant cosmic dances. As we explore the elegant simplicity hidden within these complex objects, we discover that black holes are remarkably uncomplicated beings. According to the no-hair theorem, black holes are characterized by only 3 properties: mass, electric charge, and angular momentum, which is the spin. Everything else about the matter that formed the black hole, its chemical composition, temperature, magnetic field, or any other complexity. All black holes with the same mass, charge, and spin are absolutely identical. This simplicity is profound. You could create a black hole from hydrogen, iron, antimatter, or even pure energy. And as long as the mass, charge, and spin are the same, the resulting black holes would be indistinguishable. It's as if the universe has a cosmic recycling program that reduces all complexity to these 3 fundamental numbers. Most black holes in nature are thought to have essentially 0 electric charge, since any charge would quickly be neutralized by attracting oppositely charged particles from space. However, they do spin, sometimes incredibly fast. The supermassive black hole in galaxy M87 spins at nearly the maximum theoretical rate, completing one rotation every few hours despite having an event horizon larger than our solar system. Think of black holes as cosmic meditation masters, having achieved perfect simplicity by letting go of all unnecessarily complexity, retaining only the essential properties needed to exist in harmony with space-time. Time dilation isn't science fiction. It's happening to astronauts today. Let's drift into that idea together. Every astronaut who leaves Earth, even for a short mission, returns home just a tiny bit younger than they would been if they stayed on ground. That's not enough to notice, that's not enough to feel. It's just a silver of time, a wrinkle in the moment, but it's real. Because astronauts orbit the planet at over 17,000 miles per hour, a speed where Einstein equations start whispering. At that speed, their clock ticks slightly slower, their bodies age slightly slower, their time flows just a little differently, by milliseconds. But in the universe, even milliseconds matter. The time difference isn't only from speed, it's also from distance. The astronauts are further from the center of Earth's gravity, and gravity, even Earth's gentle pull, slows time down. So up there, with less gravity and faster speed, time stretches and bends in a quiet balance. It's like the universe subtly adjusting the tempo depending on where you dance. There was an astronaut who lived nearly a year in space. When he returned, he was mathematically speaking a tiny fraction of a second younger than his twin brother on Earth. Not enough for a birthday paradox or extra candle, but enough for physics to smile. Because the universe keeps track of every moment. Now imagine if missions become longer, not months, but decades. Not orbits, but deep space travel. To Mars, to Jupiter, to distant moons. The difference may still be small, but noticeable. And one day, when ships approach near light speeds, astronauts may come home to a world older than they remember. The future might arrive faster for them than for the people they left behind. Imagine stepping into a spaceship, not a rocket like we know today, but one that glides effortlessly through the cosmos at a speed close to the speed of light. As you leave Earth behind, you look at your hands and nothing seems different. You blink, you breathe, your heart keeps its rhythm, but the universe disagrees. Because the faster you move, the slower time flows for you. It doesn't just feel different, it is different. Your cells age slower, your thoughts stretch differently, your clock ticks at a calmer pace. So if you travel the stars and return home one day, your friends may be older, decades older, while you've only lived a few years. That's not fiction, that's physics. Now imagine something even stranger. You don't need to move fast to slow time. All you need is gravity. The stronger the gravity, the slower the time. Here on Earth, your head ages just a tiny bit faster than your feet, because your feet are closer to the gravity at Earth's center. The difference is invisible to us, measured in fractions of fractions of fractions. But it's real. Put a clock at the top of a mountain. Put another at sea level, and the mountain clock ticks just a little faster. Gravity isn't just a force, it's a sculpture of time itself. Now, drift deeper with me toward the darkest giant of the universe, the black holes. Their gravity is so strong that the fabric of space and the fabric of time begin to stretch, bend, and slow. If you orbited close to a black hole for what feels like an hour, years, even centuries, might pass everywhere else. A black hole is not just an object, it's a clock that runs differently from the rest of reality. Time slows as if caught in the gravity of sleep. And finally, the question physics whisper about: if time slows in extreme gravity, if space-time bends to its breaking point, if the rules we know fall silent beyond the event horizon, could falling into a black hole lead to an ending, but to somewhere else? A different region of space, maybe? A different slice of time? A new universe entirely? Some theories say yes, some say no. Some say the truth is stranger than either answer. The universe does not rush, it reveals its secrets. And maybe that's the point. And that brings us to the end of our journey through 100 facts about black holes. The cosmic vacuum cleaners we fear, admire, and secretly want to know way too much, but while laying awake at 2:17 a.m. If your brain feels a little heavier with knowledge, and your eyelids feel a little heavier with sleep, then tonight's mission was a success. Black holes are mysterious, unpredictable, and completely unstoppable. Kind of like the moment sleep finally catches you after wrestling with your thoughts, or like the universe itself, expanding quietly, endlessly, at its own pace. If you enjoy drifting off with us tonight, if your imagination traveled a little further, or your anxiety traveled a little less, then make sure to subscribe to Bedtime Black Holes, where the universe gets quieter, the facts get stranger, and your pillow gets infinitely more comfortable. Tap subscribe, hit the notification bell, and tell the algorithm we are worth pulling into its gravitational field. Thank you for spending your night among the stars with us. Sleep deeply, dream softly, and remember, the universe is massive, mysterious, and waiting for you to explore it again tomorrow. Good night, traveler. Good night, space-time. And good night, black holes. Whatever you're doing out there,